Okay, we're going to have a look at dimensioning now. This is an extremely important topic, along the lines, of course, with the views, orthographic views, in engineering drawing. But in my experience, both personal and and from a teaching point of view, and then also from a practice point of view, the drawings, the views, I should say, are not really what trips people up. What engineers on both sides of the manufacturing fence, that is to say, on in the design end and on quality control in manufacturing, um, the real sticky point is dimensioning. Um, so uh, so this is always a very important topic with a lot of good information. All right, so let's jump in. Um, so we're looking at the dimensioning side of things, but let's take a step back and kind of understand what a drawing is trying to do. What is the intention or objective of an engineering drawing? Okay, so an engineering drawing is, as it says here, a complete set of instructions for the manufacture of a part. Okay, so complete set of instructions is key, but also for the manufacture of a part. So we're not drawing just for the sake of drawing. We're drawing so that we can convey, communicate information to somebody else or to a group of people so that they can then turn around and make the part that we've designed. So really, a drawing is a document intended to communicate design ideas, design intent. So it needs to be very clear. Okay, and we're not communicating that obviously with words, with a narrative, so to speak. That would be very, very difficult to do. And it would be open to a lot of interpretations, and we'd have difficulty with language and stuff. So instead of using words, we opt to use a kind of a graphical language, right? We will describe our part using a shape description, right? And the technique that we use is orthographic projection because that way we can accurately display our three-dimensional object in terms of two dimensions so that it fits on the sheet of paper. Fits not size wise, but the paper is two dimensional, so we're limited, so we can work within the limitations of the medium that we're using to communicate paper. Even a computer screen, we're really not going to be um, uh, doing much with, or there isn't much done with three-dimensional drawings in terms of manufacturing and stuff. But then after the shape description, we need to describe the size. So just describing the shape isn't good enough because we don't know how long something is, how thick it is, what the diameter is, how deep it is. So that's where size description comes into play, and that's where dimensions are used. So so really these instructions are a shape description, a size description, and then any additional notes. Okay, any additional notes to help describe things that aren't, um, easily described with shape or size. All right, so those are the three things that a engineering drawing is trying to do. Okay, so the engineering drawing then has two objectives: to describe the shape of the part to be manufactured and to describe the size of the part and its features to be manufactured. Dimensioning accomplishes the size description. And here we have an example of a drawing with a clearly defined shape, right? We can see that it's a cylindrical part. We can see in this view that it's cylindrical, circular, right? And we can see in this view that it has a series of kind of a stacked cylinder arrangement, right? We have a smaller cylinder here with a diameter of 80. We have a larger cylinder here which is dimensioned with a tolerance of 127 to 126.95. We also see that we have a hole in the center, and the hole in the center we can see by the drawing here is tapped or threaded. Okay, and there's some detail here. We actually have counter bore, which kind of opens up to the threads here. The counter bore has a chamfer on the front end here, and then there's a relief on the back end of 0.4 millimeters. By the way, this is a metric drawing. Okay, we can see that right down here. It says metric. And we also see that there's 4 holes around the perimeter, the larger diameter, and these holes are also tapped. We can tell that with this dimension, right? So we have 4 holes with a diameter 8.2 millimeter hole, but then they're tapped. So this is the tap drill, and then they're tapped with a thread that would be an M10 by 1.25. So an M10 is a 10 millimeter diameter tap, 1.25 pitch, 1.25 millimeters between each thread, and 6G is the tolerance on that thread. Okay. So this is a drawing. This is what we would call a detail drawing because it shows one part, and it's complete in terms of its shape description and its size description. Does it have any notes? Well, it has some notes down here. There's a revision, right? So at letter A, which is right here, this diameter was 82 millimeters, and it was revised by TJ on 1996 to be 80 millimeters. Okay, so that's some notes. We also see a note here that says metric, and there's a note here, limits on machining dimensions plus or minus 0.4 millimeters. So notes kind of take the place of either shape description or size description, depending on what's needed at the moment. There's also local notes. Local notes. This would be a general note because it applies to the whole drawing. This would be a local note because it applies only to this feature that's pointed at, and it says break the corners with a radius 0.4. So basically, just break the sharp corner so that it's not a sharp edge. We see that this is a chamfer. Okay. We see that it says finish all over, which means that we want it to be machined all over so that it's smooth. Okay. So this is a good example of a detail drawing, shape and size description complete with notes. All right, so how are we going to dimension, right? We have this 3-dimensional part. We've figured out how to show it 2-dimensionally on a sheet of paper using orthographic views. How do we start dimensioning? Well, we're going to follow a 2-step procedure for dimensioning. Okay, nice and easy, 2 steps. The first step is to dimension the sizes of individual geometric shapes of the part. Okay, 3-dimensional geometric shapes. Step 2 is to dimension the location of those shapes with respect to mating surfaces and functional requirements. Now, this underlined part here, with respect to mating surfaces and functional requirements, is a challenge, right? Because this, in order to do step 2 properly, we must know where the part fits in the machine or mechanism, in the assembly. This is often not the case when you're learning how to dimension. All right, we don't. Oftentimes, we work with individual parts. We don't work with a part that we know where it fits in the assembly. Not only that, but in order to really properly dimension it, we would know what the function of that part is, how it's going to be used. You know, whether it's going to be under stress, whether it's going to be rotating, whether it's going to be, you know, there's high friction, whether there's high heat, all that good stuff. So step number 2, the underlying part, is a challenge, okay? But definitely step number 2, we can approach that and we can, you know, kind of understand how we should be approaching that. Step number 1 is a little bit more straightforward, okay? Dimension the sizes of individual geometric shapes. So what are we talking about when we talk about these individual geometric shapes? Well, actually, with the exception of kind of curvilinear, you know, sweeping surfaces, we can break 3-dimensional objects down into a collection of these geometric primitives, right? These are primitives, all right? So these primitives include a rectangular prism, right, which is a rectangular box. It could be square, but, you know, rectangular is the general shape here, right? A square box or a rectangular box. A cylinder, right? A pyramid, and in this case, we could have it truncated, right? Truncated means it's chopped off at the top, or not truncated. We have a wedge shape, and then a cone, which could also be truncated, right? So we have these 5 different shapes. There's actually 7 total primitives that we could use. There's 2 that I left out here. That would be a torus, and a torus is a donut, right? Donut shape, and then a sphere, right? So of those 7 shapes, we could put them together to make any 3-dimensional object. Now, we have to understand that for each positive version of a primitive, there's also a negative version of a primitive, right? So a positive cylinder is a cylinder that we can touch. A negative cylinder would be a hole, okay? A rectangular prism, a positive shape would be a square, a box, right, that we can touch. A negative shape would be a square cutout, a rectangular cutout of an object. Okay, so each one of these 7 primitives, the 5 that I'm showing here, plus the other 2, can take the form of a negative shape or a positive shape. All right, and what we're going to do with these shapes is we're basically going to break down the complex 3-dimensional object that we're trying to dimension and draw for our engineering part. We're going to break it down into these geometric primitives. Okay, and we do it like this. So if we have a part that looks like this, we've kind of broken this down. You can see that what is it made up of? Well, it's made up of a cylinder, a positive cylinder, right? We have a positive rectangular prism here, and we have another positive rectangular prism here. So those 3 shapes are, kind of glued together or welded together, or however, it doesn't matter, but we're breaking them down. We also have 4 negative cylinders here, right? And here we have another negative cylinder right there, and we have another negative cylinder right here. And heck, we even have a negative cylinder right there, or you could just say it's a continuation of that. To make this opening right here, we actually have a negative cone, right? So we can break this object down into a collection of positive and negative prisms, or excuse me, positive and negative primitives. Right? And then this is going to help us with our dimensioning. So here's the 2-view drawing of this object. And you can see, just ignore the location dimensions right now. You can see the size dimensions for the primitives. For the rectangular part right here, we have how many dimensions? Well, we need 3 because it's a 3-dimensional shape. So we have a length, a depth, and a thickness, okay? For this little prism right here, we have a length, a depth, right? And you can get that by this dimension minus this dimension, right? And then the length of it, or the depth of it, is shown right there, right? For the holes, we have this dimension for these 4 holes. We have this dimension for this hole. We have this size dimension for that small hole. The cone is dimensioned with this size dimension and this angle. Okay? And so on and so forth. So the key is to understand, to break the parts down, and then to dimension the sizes of each individual part. Because each individual part, if we go back to these are very simple to dimension, right? They're 3-dimensional primitives, and so they basically have 3 dimensions, right? The prism has a length, a width, and a depth. The cylinder has a diameter and a height, or depth, right? The diameter kind of takes the place of 2 dimensions, right? So if you're wondering, hey, what's up? This is a 3-dimensional shape, but there's only 2 dimensions. Well, the diameter is a 2-dimensional, a surface dimension. So it's 2 dimensions wrapped into one, right? And we can go on and on here, right? A cone has a diameter and a height, right? That's all we need, right? Considering that it's a right cone, right? If it's off center, if it's not a right cone, then we need another dimension for the misalignment of the center, all right? All right, so let's do some examples here. All right, so in this part right here, we have a rectangular prism, a horizontal, a rectangular prism, a vertical, two holes here and a hole here, negative cylinders, a positive cylinder here, and then a negative cylinder going through that. So in terms of the size dimensions, right, we have the size of the horizontal part, right, which is going to be shown. Look at that. They're missing that, right? Right there. It should be shown right there. I'll have to go back and add that. How dare them? This is taken from a book, by the way, so that's a little bit of an error. But we do have the width right there, that size, and then the thickness right there, that size. How about the vertical one? Well, we have the height right there, that size. We have the thickness size, and then we have, again, the same dimension for the width. For the holes, we have 2 times diameter size, right? 2 of these, 1, 2, so that's a size dimension, all right? We have 1 size dimension diameter here for that one. Oh, by the way, these holes, how deep are they? Well, right there, right? So again, if you're keeping track of the dimensions, we're going through primitive by primitive and making sure that we have the required dimensions. We're ignoring where they're located, right? That's a location dimension. So we don't worry about that yet, okay? We have a positive size dimension for this cylinder and a height right there, right? And then that's it. Now, when we turn our attention to location dimensions, you can see that we have, we need to locate this hole and cylinder, right? So we locate it from the back edge here and we locate it from the side. Notice for location dimensions, we really only need 2 dimensions. Why? Well, because each view only has 2 dimensions in it. Each view is a 2-dimensional view. So how about the location of these holes? Well, location up to here, and location from this end, location for the first one, and the location from the second one based on the first one. Okay. So that's a simple part with a geometric breakdown. I encourage you to practice this yourself, right? Cover this side up and have a go at this, right? And first try to draw the views, sketch them out, and then go back to dimension it. All right, so when we look at this as another example, what do we have here? We have a basic shape. We have a rectangular part, right? It's interrupted by this half cylinder here, which we can really define as a cylinder. We don't need to get into half cylinders and stuff. You know, you can define a half cylinder as a cylinder with a radius. That's all it is. And then we have a negative cylinder right here, right? So when you're looking at this one, I would not break this up into a rectangular prism here and a rectangular prism here. Instead, what I would do, thinking along the lines of maybe if I was making this out of wood, right? I would take a long piece of wood here and I would cut that out, right? Instead of trying to glue this with 2 smaller pieces here. Then we have a vertical prism right there, 41 by 48 by 11 thick. And we have a negative. Now, how is this constructed? Well, we have a negative cylinder right there. Again, don't get hung up on the fact that it's not a complete cylinder. It is a complete cylinder. We're just missing the top of it. Doesn't affect how we dimension it. And then see this shape right here? That's a negative prism, right? It's a square shape. And so when you break this down into those parts, this is actually a pretty straightforward, simple part, right? We have negative cylinders here, another negative cylinder here, and then that's it. Some of the other shapes we can take care of with notes. So fillets, radius 2, right? Just notes. This front curved surface, round, would be just a radius 13, right? And this surface right here would be just a radius 6 or 5, I think, right? So if you start to see these what to first glance would be a complex part, if you start to break them down into simple three-dimensional primitive shapes, you can start to understand and approach dimensioning from a much more basic, simpler, step-by-step sequential context. Again, this shape, we have a cylinder here, and a cylinder here, and a cylinder here. So we have 3 cylinders separated by a certain distance. We have a negative cylinder here, and a negative cylinder here, and a larger negative cylinder here. How do we handle the sloping surfaces? Well, we don't need to. If we know that this surface and this surface and this surface and this surface are tangent, then we really don't have to dimension it, right? The view describes the fact that it's tangent to this large cylinder and tangent to this cylinder. All right, so continuing with this idea of the dimensioning, what we're talking about really is making sure that our dimensions are functional, okay? Functional dimensions are dimensions that suit the function and mating relationship of the assembly, which is really the king, right? That is the most important objective, right? We want to produce parts that work, and in order to produce parts that work in an assembly or a machine, we need to make sure that they're dimensioned properly so that they're made properly, right? We don't want holes that are too large or too small. We don't want surfaces that are out of alignment. All of that is taken care of with dimensions, okay? Dimensions and tolerances. Mating part dimensions are those dimensions that are assigned based on the features of the mating parts in the assembly. Okay, and this is where we get into a little bit of a sticky problem, because we don't often know what the mating parts are. Okay, so for example, in your assignment, in the drawing of the door bearing, we don't know where the door bearing fits in with whatever it's mating with. I don't have that. You don't have that. Same thing with the with the other parts. Okay. Now, on the caster assembly, we do know what each part is and where it functions. Okay. We're not dimensioning those parts, but just to use that as an example. All right. So functional dimensions reduce dimensioning mistakes. They reduce the time for dimensioning. They make the dimensions functional, i.e., serving a purpose towards a higher objective. We have also functional tolerances, which are critical. Even though we're not talking about tolerances in this class, I'm sure you will in other classes that you take. Tolerancing is especially critical because they indicate what manufacturing operations are going to be used, and they have a direct relationship on the cost of the part. The tolerances do. It gives us better assemblies, and which means cheaper parts. Okay, so kind of an example of mating part dimensions is this simple assembly where we have this block that goes into this kind of slot, and then we have these 2 bolts that pull this and assemble this, finish the assembly. What I would like to do is to impress upon you the idea that mating parts come in only 2 flavors, right? We either have cylinders, we either have pins and holes, shafts and holes, right? Cylindrical mating parts, or we have slots and rectangular prisms, right? So here we have this can be viewed as a kind of like a pin, right? Or a shaft, right? Because it goes into, what is this? This is kind of like a rectangular hole, right? This is a negative feature. This is a positive feature, and they go together. In the same way that this is a positive feature, and this hole is a negative feature, and they go together. So if we can start to break things down that mate together as either rectangular mating parts or cylindrical mating parts, then again, we've simplified things, right? We've given ourselves a context in which to understand our complex assembly from a much simpler point of view, right? Which is going to help us understand it, break it down, and all that good stuff. So these mating parts, here we have a rectangular mating part going into a negative rectangular feature. Positive cylindrical features going into negative cylindrical mating features. From a dimensioning point of view, you dimension the diameter of the bolt in this case, and it goes into the diameter of the hole, right? So those are mating dimensions. Same thing here. We have this would be similar to the diameter of a bolt of a pin, right? Even though it's one dimensional. And it mates up with this dimension right there. So these two are mating dimensions. This dimension right here for location, the location of the edge. Why is this edge so important? Well, this edge and this edge are mating. And so this dimension and this dimension are mating dimensions. Same thing here. The distance between the holes here and the distance between the holes here. All right, so let's go over some rules for dimensioning. I'm not going to bore you with a lot of rules for dimensioning. There are, if you look at different books, they give you, I don't know, 50, 100, 75 rules, but that's getting too specific. We don't really need to focus on all those rules. We don't even need to know all those rules because there's some overriding rules that kind of fill in all the gaps and that help you understand things from a much more higher level point of view. One of the most important rules for dimensioning is the contour rule. Okay, contour dimensioning means that we dimension features in their profile or contour view. Okay, so if we look over here on the right hand side, this is where we see bad dimensions. Okay, so this 20 millimeters for this, see the feature that we're dimensioning? It's kind of hard to understand what it is, right? In this view, we don't see much of this feature. We see this feature in this view right here. This dimension should be applied in this view as we see it right here. Okay? Again, this 28 for this slot. Well, we don't even know whether it's a slot. It could be a lot of different things. This is a very poor view because we don't see the contour of this shape, the profile of this shape for the 28. Where do we see the profile of this? Right here, right? So we really should be putting this 28 up here, like it is right there, okay? So I encourage you to go through this drawing, cover up this side, and just mark the dimensions that you don't feel are following the contour rule, and then reveal and see if you got it right. Okay, a couple other rules, important rules. For efficient and clear dimensioning, we must eliminate redundant dimensions. Features shall only be dimensioned once in a drawing, and the same feature in different views is still only one feature. So do not dimension the same feature in different views. And we want to eliminate superfluous dimensions. So we don't want features that are dimensioned in two different ways. So for example, let me go back to this. Okay. So what would be an example of a superfluous dimension? All right. Well, let's say that we have let's leave this 20, even though the 20 is wrong up here. Let's leave this 20 up here and the 38, right? So if I dimension the distance from here to here with an 18, so I end up having a 20 dimension here, I end up with an 18 dimension here and a 38 dimension here. That's a superfluous group of dimensions. One of those dimensions is superfluous. Why? Well, because this surface, I can get the location of this surface by either coming 20 millimeters from this back edge or by traveling 18 millimeters from this front edge. Therefore, I can get the location of this surface two different ways. And that's why it's superfluous. And that's why the 18 is left off here. All right. So that's what a superfluous dimension is. All right, so continuing with our rules, we want to dimension cylinders in their diameter with a diameter in their rectangular view. Okay, we want to dimension holes with a diameter in their circular view. We want to dimension curves with a radius in their circular view. We do not dimension to hidden surfaces or features. That's a big no-no. Don't dimension to hidden surfaces or features. Find a view in which the feature is not hidden and dimension it there. Dimension features where there are shown true shape, right? So if a feature is distorted, then maybe you need to use an auxiliary view or just find another view where it's not distorted. Do not cross dimension and extension lines. I'll show you what this is in a second, what a dimension and extension line is. Dimensions shall not specify the manufacturing method to be used. So we don't want to say something like drill diameter 9, right? We leave the manufacturing method up to the manufacturing professionals. And we want to make use of symmetry if functional. All right, so here's an example. So this is for another rule. We want to dimension outside of the views. This is not appropriate. But this is also a good way to show, this is an example of crossing dimension lines. So that's a dimension line and that's a dimension line. These, by the way, these lines here, these are extension lines. This is a dimension line. So the dimension line is what is the line in between the arrows. An extension line is the line that comes off of the object and goes out and is on either side of the dimension line. So we can cross, do we have any here? No. We can cross dimension lines and extension lines, but we cannot cross dimension lines. Okay. Symbology. We want to use standard symbols. Okay. This is a short kind of display of common standard symbols. We have the counterbore or spot face symbol, the countersink symbol. These dimensions, you don't really need to worry about this because AutoCAD and Fusion do these automatically. So this is only if you were drawing it by hand. Okay. We want to use standard symbols for counterbore holes, countersink holes, spot face holes, tapped holes, repetitive features. So a repetitive feature would be these 4 holes. So we can dimension 4x, 4 times diameter 0.375. Now it's important here, the spacing. Notice that there is no spacing between the 4 and the x. But there is spacing between the x and the diameter symbol. All right? So that means 4 times diameter 0.375. Here's examples of a counterbore hole, diameter 10, counterbore diameter 20, depth 8. So this diameter across here is the diameter 20. This is the diameter 10. The depth 8 is the depth of the counterbore. The countersink symbol, diameter 10, countersink diameter 20, and 90 degrees by 90 degrees. Notice the space on either side of the x here because this x is used as a by, not a repetitive feature. All right. So here the diameter 10 is this through hole. The diameter 20 is the large opening for the countersink. And then the 90 degrees is the included angle of the countersink. Spot face is very similar to the counterbore. Dimensioning a blind hole. So a blind hole is a hole that doesn't go all the way through. So we dimension a blind hole with a depth symbol, right? So this is 20 millimeters deep right there. Diameter 30, 20 millimeters deep. Notice that we do not include the uh, the the cone tip that is generated by the drill bit, right? So that's a feature, that's an artifact that we need to show on a drawing if we have a blind hole, unless it's made by a a flat bottom drill, right? But we don't dimension to that. That's not included in the depth. Chamfers, okay? So negative chamfers or chamfers on holes can be dimensioned like this or like this. External chamfers can be dimensioned like this or this. This is actually preferred. Notice again the spacing between the x. When we use x as by, we have a space preceding and after. So this says 2. This is, how do you read this? Is this 2 times 45 degrees? No. This isn't times. This is by. So this is 2 millimeters by 45 degrees, which means this distance here, you can see it up here, is 2 millimeters. This would be 2 by 2. So 2 millimeters here by 2 millimeters here. Slots. All right, so here's 3 examples of how we dimension a slot. This, by the way, is not preferred, even though it's appropriate. I mean, it's okay. It's not preferred. Okay. Notice here that we include a 2 times r. Am I missing the dimension here? No, I'm not missing the dimension. This is meant simply to imply or to inform that this is a circular radius, and there's 2 of them. All right, so we don't put a number here. Why not? Well, because that would be redundant. We have the 10. So the radius here is already, we know that as 5. So the 10 here means that we don't put a number here. 10 here means that we don't put a number here. If you put a number here, then you got to get rid of the 10. All right, so here's an example for you to work out. All right, I'll leave this for you. Right? I'm not going to do this for you. On the next slide is the answer. All right. So again, try this by hand. Right? And then you can do the answer on the next slide. There we go. I'm going to go through that fast. All right. Here's another problem for you to work on. All right. So again, try this. All right. If you really want to practice. You can sketch this. Sketching is a good skill to have, and you can practice your sketching of this. If not, you can just print this page, and then you can try to use our 2-step dimensioning procedure. Dimension 1 for size, 2 for location, and then include your standard symbols and notes. There's your answer. Okay. So let's move on to dimension units. Okay. So we dimension in either the decimal inch system or the metric system, and the standard unit for metric system is millimeters. All right. There is a difference between the decimal inch system and the metric system in terms of how we display those dimensions, those units. Okay. So for the decimal inch system, whole numbers show a minimum of 2 trailing zeros. That is, zeros to the right of the decimal place. Numbers less than 1 have no leading zeros. So and I'll show you an example of this. So I'm not going to do that right now. I'll show you an example. For the metric system, we do the opposite. Whole numbers from 1 to 9 are shown without trailing zeros. Numbers less than 1 are shown with a leading zero. So what does that mean? Well, here. So for the decimal inch, right? No leading zeros. So it's 0.500. That's a leading zero, not 0.5. Trailing zeros, we include 2 trailing zeros. So 10.00, not 10. For metric dimensions, the opposite. Leading zeros, yes, we include a leading zero right there. No trailing zeros. So 10, not 10.0. All right. Yeah, I'm kind of covering up that. I'm sorry. That was supposed to be animated, but bolts and screws. What's the definition of a bolt? A bolt is intended to be inserted through 2 or more clearance holes and be fastened with a nut. So by definition, a bolt includes a nut with it. A screw is intended to pass through one clearance feature and be threaded into another feature. Are there variations on this? Absolutely. You can thread a bolt into a threaded hole, and screws have nuts too. All right. There are slight variations on screws. There's cap screws and machine screws. Machine screws typically have finer threads than a cap screw. Again, these definitions are kind of they've gone to the 4 winds, right? Because everybody just uses these interchangeably, right? But officially, these are the definitions. When we're dimensioning fasteners, threads, there is a standard way that we represent those dimensions. For inch threads, we're going to include notation for the major diameter, the thread form, that is the shape of the thread, the thread series, that means the number of threads per inch, the thread class, so how it fits with a mating thread, the head type, and the fastener length. So these are the 6 ingredients that a thread dimension, a fastener dimension, must have. So, for example, here is a tapped hole. So it's 0.25-20 UNC-2B LH. So what does this mean? Well, the 0.25 is the major diameter. The 20 is the threads per inch. The UN stands for Unified National, and that's the profile or the shape of the thread. C is a coarse thread for the form. 2 represents the class of fit. It can be a 1, 2, or 3. B is for an internal thread. A means external thread, and then LH is a left-hand thread. So that's a complete dimension for a inch thread. For an external thread, the only thing that changes is the A out here. So instead of B for an internal thread, we get an A for an external thread. Right? Obviously, this thread is not going to go into this hole. Why? Well, it's a 1/4 inch major diameter, but notice that this is a finer thread. This is 28 threads per inch. This is 20, so that's not going to work. We also see that this is F for fine. This is C for coarse. The thread note standard that we would include on the drawing here with this shape or this part would be an ASME B 1.1-2003. So that would be included in our drawing. For metric threads, it's different. Okay, we still are going to lead with the major diameter, but then we're going to the thread form is kind of included in that. You'll see, and then instead of threads per millimeter, or threads per inch, we give the pitch, which is 1 over the threads per millimeter. And then there's a tolerance, head type, and fastener length. So an example here for an internal thread would be M10 by 1.5-6H LH. So the M is a metric thread form, 10 is the major diameter in millimeters, by 1.5 is the pitch. So that means the distance from thread to thread is 1.5 millimeters. 6H is the tolerance, and LH for left hand. Notice here that there's really no difference between an external and an internal fastener in terms of the metric thread. Right? There's nothing that indicates that this is a external fastener except the fact that you're pointing at an external thread. And then again, the note that you would include on the drawings here would be ASME B 1.13-2005. That is the metric thread standard. All right, so in case it wasn't clear before when I was talking about clearance holes and tapped holes, a clearance hole is a hole that you can drop the bolt or the screw through, right? It's not going to be tight. It's just going to go through. A tapped hole is a hole that has threads cut in it. When we're drawing a clearance hole and a tapped hole, this is how we draw this. So this is an assembly drawing with 2 clearance holes. Notice that we don't necessarily have to draw the clearance, the gap in here, right? That's not necessary. Oftentimes it is shown simply because you can see it, right? Here, the tapped hole, this is drawn using what's called a schematic representation for the threads, right? And so we don't show the tapped hole threads because it's consumed by the tapped fastener threads. So finally, in our whole design, there's a few dimensions that we need to know of, right? So when we're designing for a tapped hole, typically the operation would be to drill a hole this deep, right? So this is the drilled hole depth from here to here. Then we tap, and this is the part that's tapped. This is a clearance hole, so this is the part that's tapped. We tap a portion of that, and when you tap the hole, it's going to open it up to a larger diameter because you're cutting threads into the material. And so then this is the thread depth. And then we have the tip for the conical tip from the drill bit on the end. The fastener is going to go down this deep, right? So that's the fastener depth. Okay. Now, in our assignments, we're not doing anything with threads, so this is just extra stuff for you to be aware of. So we're not. I don't even think in any of the dimensions for the assignments there's any thread dimensions. So I think you're off the hook there. All right. So that concludes our dimensioning lecture. Remember that there are some practice work that you can do in this. Print out those drawings, cover up the answer, and have a go at it yourself. Keep working at it until you get good at it. Dimensioning is a definite skill, and it's an important skill for designers to have. All right, I'll see you in the next video. Bye-bye.